I'm Grace Sommers. I'm going to be talking about this work that I did with some people that I'll show on the next slide about fault-tolerant thresholds with concatenated codes. So, as promised, these are my collaborators. This was done with my advisor David Hughes at Princeton, also Michael Gollins, who's in the audience, and Michael Fosfig and David Hayes at Continuum. And it's a preprint that came out on Monday. So why concatenated codes, or like why was this something we chose to explore? So code concatenation is a way to sort of build up a good code in a sort of hierarchical or tree-like structure. And this strategy is what underlies classic proofs of the ability to have a fault tolerance threshold. And you can view it as being like an alternative paradigm to using surface codes that have magic state distillation, or as we heard yesterday, magic state cultivation. And just to give you a picture of like what a concatenated code is, a very simple example is Shore's 9-qubit code, which you can view as concatenating a 3-qubit bit flip repetition code with a 3-qubit phase flip repetition code, as I showed in this figure here. But despite a lot of experimental advances that we've been hearing about in this workshop that have led to a lot of progress, particularly with surface codes, the observation of a fault-tolerant threshold with concatenated codes has not been demonstrated on hardware until this work. So I'm going to today tell you about how we explored these fault tolerance transitions in both theory and implemented it on quantum device. So what do we want to be able to see a fault tolerance threshold with concatenated codes? So there's a few things on our wish list. So one would be that it would be nice that within this tree structure of building up the concatenated code that we have some small base code so that we can actually see on near-term hardware many generations of concatenation. We also want a protocol to be able to prepare these states and decode them in an efficient manner and a fault-tolerant manner. And ideally, we'd want an experimental platform that has all-to-all connectivity and mid-circuit measurement so that we can implement these non-local interactions in this growing tree. And we would also like to show not just state preparation, but also a quantum memory and the ability to do logical gates. And so this work, we basically knocked off these items on this checklist. So I'm going to present to you about, so in this talk, I'm going to tell you about this code that we've been studying called the generalized Shor code, which uses only a base code of 2 qubits. I'm going to describe to you this state preparation protocol that's based on something called a multi-tree that doesn't involve any ancilla overhead, and I'll touch on how we decode this circuit. And then I'll describe how we actually implemented this on hardware, and time permitting, I'll show you some theoretical work looking at quantum memory and magic state preparation. So just to make sure we're all on the same page, the way I like to think of it is that a concatenated code is really just a tree. And in particular, concatenated stabilizer code is a tree where all of the gates on the tree are a Clifford gate. In particular, if we take a B-ary tree, so in this example, B is equal to 2, and each node of this tree is an isometry, then this, like if we have T layers of this tree, then that gives us an encoding isometry from a 1-qubit logical state that we feed in on the root to a B to the T qubit physical state that we have on the leaves. And something that's sort of remarkable is that even with a binary tree, you can get an exponentially growing code distance if you choose this local isometry to be something, if you choose it appropriately. So in particular, something that we studied along with Yadavali and Marvian, who are also here, is this code that I'll call, for the purpose of this talk, a generalized shortcode, where, similar to 9-qubit shortcode, we're going to alternate between a bit flip and a phase flip repetition code, but we're just going to do it with only 2 qubits at a time. So we get this binary tree. And this makes a CSS code, namely one that, if you look at the stabilizers, you can choose them to be only X or only Z. And it has a distance that's growing like a square root of the number of qubits. Now, of course, the errors can occur like anywhere in this encoding circuit. That's why we need fault tolerance, or that's the basic job of fault tolerance, is to deal with these errors. And in particular, in the circuits that I'll be describing, we could have errors, say, on each of these fresh qubits that are being fed in at each layer. They could be occurring after 2-qubit gates, and they could also be occurring on the measurement outcomes, like when we read out the syndrome. An example of a error channel that we'll consider is that's particularly appropriate for since we're studying CSS codes, is to think about independent bit and phase flips, where so basically each of these explosions is composing a bit flip channel with a phase flip channel at some rate p. And later in the talk, I'll describe some other noise channels that we also are considering. So let's say we have this tree circuit, and we run this circuit from the root to the leaves, and then we measure out a syndrome on the leaves. How are we going to decode that syndrome? Well, it's actually quite easy. So the basic idea for any decoding task is we have some syndrome, we're going to find some error that will return our system to the code space, and then we're going to choose the most likely logical class relative to that error. So should we take that error and multiply it by a logical X, a logical Z, a logical Y, and so on? And once we've made that choice based on, say, contracting this tree tensor network, we would say that we've succeeded if we actually didn't implement a non-trivial logical on our system. So, for example, if the logical state has suffered a logical bit flip after our chosen correction operator, then we would have suffered a logical X error. And so in this single tree scenario where we only measure the syndrome on the leaves, we found that there is a phase, a so-called coding phase, at low rate of error, such that below some noise threshold, you can partially succeed in your decoding, meaning that you will converge towards a failure probability which is less than 1/2, say, for probability of getting an X error, like I've shown in this figure here. And so, okay, that's nice. We could even take this now, and if we wanted to prepare a logical state that was converging towards 0 failure probability, we could say do some sort of state distillation. But we're going to take, in the rest of this talk, I'm going to describe a different approach that's going to be able to drive that failure probability down to converge towards 0 in a coding phase, so to speak. So first I'm going to describe how this works in theory. And so the basic idea is we're going to replace that tree circuit that I showed earlier with a multi-tree. And so in particular, what we're going to try to do for this experiment is prepare a logical state, either a logical 0 or a logical plus state. And using this circuit that I will describe a little bit more in detail on the next slide, you can see, though, that it uses a constant number of qubits per layer. So in the tree circuits, you start with only 2 qubits and you end up with like 2 to the t qubits. Here, you start with 2 to the t qubits and you keep that number through the circuit. Why do we particularly want to prepare these logical states? Because we're going to use them later for doing Steen error correction. So in particular, if you wanted to prepare a logical 0 state, then for each of these magenta legs, you would feed in a 0 there. And then in the very last layer, you're allowed to do perfect stabilizer measurements just because we're just analyzing the performance of this fault-tolerant gadget sort of in isolation. And yeah, so why have we gone to this multi-tree? The idea is that what we're doing at each layer is actually performing syndrome checks between two identically prepared states in each layer of the encoding. So each of these square boxes is really doing a transversal CNOT between two blocks that are encoded the same way, measuring one of them, so that's the ancilla that we're going to measure in some basis, and then using that ancilla that we've just measured, we can then reset that and feed it into the next layer of the encoding. So these solid black lines that I've shown in this picture is showing the sort of the system growing as a tree, and all these dashed lines are the ancillas that are used at various levels to check how are we doing on the preparation of this system. Okay, so I told you how to decode a tree. How do we decode a multi-tree? Well, the main difference is that now we have a syndrome measured in each layer, not just on the leaves. We still want to find some Pali operator that's going to return us to the code space, and we still want to calculate what is the most likely logical coset of this Pali operator. And because we're only doing state preparation here, we only care if the logical state gets flipped. So for example, if we're preparing a logical 0 state, we don't care if there's a logical Z error, that has no effect. So we're really just choosing between two logical classes. And in principle, you can calculate this most likely logical class by mapping this faulty circuit onto something called a space-time code, which is a subsystem code. And there's certain cases where you can actually do this, bless you, do this exactly. A case where you can do this exactly is when the noise is heralded. So I showed you before that standard bit flip, phase flip error channel, but the problem there is you don't know where the errors are happening. You just assume every location could have, like this is subject to the same channel. In a heralded noise channel, you're told that each qubit at every possible error location, either you flag the qubit and it's subject to some channel, or if it's not flagged, then we know for certain that it didn't suffer an error. A standard example of a heralded noise channel would be an erasure channel where the flag, if the flag is set, then that means you just completely lost that qubit and it got replaced by a fully mixed state. There's some experimental motivation for considering this type of channel. So in addition to being on the theoretical side, it makes our decoding easier. On the experimental side, there have been these erasure conversion protocols. I believe we're going to hear about one later today. That managed to convert most errors into being erasures, because with the motivation that they're easier to decode. So if we take fully heralded erasures, we can optimally decode using the space-time code formalism, and we get the results shown here. So the x-axis is on the left is the rate of erasures at these various locations, and I'm showing the logical failure probability averaged over logical 0 and logical plus. And you can see that it has a crossing around 0.089. We can also, because I like statistical mechanics, I want to fit everything to a scaling collapse. So here I did this just one parameter scaling form, and you can, for this particular noise threshold, you can then see that like the transition gets broadened at finite system size by this exponent nu, which is approximately 2.85. Okay, that's all well and good, but I told you that we did this in the experiment, so let me get to that. So our experimental setup that we're considering here is on the Quantinuum system model H2. At the time of this talk, it now has 56 qubits. At the time of the experiment, it only had 32 qubits, but that was good enough for us, because I only care about powers of 2. Importantly, it has all-to-all connectivity, so it's going to allow us to do these 2-qubit gates that are on far apart qubits. There's obviously some noise in this device that's not heralded. We're going to model that as being independent bit and phase flips just for the purpose of our decoder. And importantly, this noise rate is well below the threshold for unheralded errors. So I showed you the threshold for heralded errors. The threshold for unheralded errors is around like 0.015. So we're well below that, and we just have these gate errors and some measurement errors that we have in this device. So okay, we want to see an actual transition. So what we're going to do is actually introduce errors like to make the most of this, to see a convincing fault-tolerant subthreshold phase. We're going to choose these errors to be heralded just so that we can boost the threshold that we actually see. But it's important that we do have some unheralded errors lurking there that we can't control. So okay, so how are we going to deal with these unheralded errors? Well, unfortunately, we can't decode the multi-tree exactly. Because you could view it as a tensor network contraction that's just way too entangled and not efficient. So instead, what we do in a nutshell is, so we're given this syndrome from round 1 all the way to T, where T is the depth of the circuit. Remember, in each round, we're using an ancilla to measure, we're pairing up like an ancilla and system and to noisily read out a syndrome. And so what we're going to do is in those earlier rounds, we're going to use the syndrome that we see to update our local error model on the ancilla. And the approximation is that we're only going to update the marginals conditioned on the outputs and not the full distribution. And then in the last step, given all the syndromes that involve this syndrome, so involve the system, so all the syndromes that are touching that solid black tree that was growing through the circuit, and also given this updated model on the ancillas, we can do the same thing, which I've said now, this is my 3rd time saying it, find an operator that returns us to the code space, choose the most likely logical coset with this caveat that it's most likely according to our approximate noise model, which is not actually, it's not exact. And it amounts to evaluating this tree tensor network. And then in the experiment, okay, how do we know if we succeed? I said we fail if the logical state got flipped. In the experiment, what we do is in that last layer, we destructively measure the system. So we learn both the final stabilizers as well as the actual logical state. The decoder doesn't know that logical state, so the decoder goes and does its thing, and then we come back and say, did the decoder get the correct logical state? So here's what we get when we add in erasure errors. So now E is this added rate of erasures. So remember, we have this background noise, and now we're adding erasures. Note to anyone that was at my poster yesterday, by popular demand, I have changed to log 10. I learned that this is a thing that experimentalists like, I guess. So this is, so we can only run a certain amount of shots on the device, so that's why the error bars are rather large, but it's also why we choose to show, so on the left-hand panel, I'm showing us tuning through this transition as we add errors, and even though we're only going up to 32 qubits, that's enough to see that there's this regime at low error rates where the logical failure probability is being reduced as we increase the system size. And I'm showing the subthreshold phase at an added error rate of 0.02. If I had done this at added error rate of 0, so like just the native noise, then with the number of shots that we have, we would just see a failure probability of 0. So it'd be kind of trivial. But okay, we see this crossing between 0.06, 0.09. It's not shifted that much from when we just had fully heralded errors, so that's nice. We can also do something that we couldn't do in the classical simulation, which is add in coherent errors. So now this is a little bit strange. If you have a coherent error, if you knew everywhere that the coherent error was, then you wouldn't have to measure a syndrome at all. But okay, because we are gods in this experiment and we're putting in the error, we choose to make them heralded just so that we can see a higher threshold. But because there's some unheralded noise that's in there as well, we do have to measure a syndrome, and then that makes it so that this is a non-trivial task. And so basically what the noise channel does is if it gets heralded, it's going to apply this deterministic non-Clifford rotation on these flagged qubits. This is something that's difficult to sample classically because these are these non-Clifford rotations. So that makes it a good thing to do in experiment. And okay, the crossing is a little bit noisier than in the previous slide, but we do see there's a regime at low added error rate. So the added error rate is now Q for coherent. You can see that there's a subthreshold phase where it's getting suppressed with increasing system size, and then there's a above threshold phase where it's increasing. All right, so I think I started a little bit late. So if I have just a few minutes to tell you about, okay, we did state preparation. Let's move towards some more difficult things. So in particular, in state preparation, it's sort of easy in the sense of we only worry about one type of error. So like if we're preparing a logical zero state, then it's essentially a classical problem because we don't care about the phase flip errors. So let's make life harder and actually do something quantum. So I told you that the reason why we prepare these logical plus and logical zero states is because we're going to use them for something called Steen error correction. So I better tell you what Steen error correction is. For the uninitiated, it's a way of reading out syndromes, particularly like if you don't have low depth, or if you don't have like a LDPC code, then you have these big long stabilizers, and you need some fault-tolerant way to read out those stabilizers. And the way to do it, if you have a CSS code, is take an ancilla that's encoded in the same code as your unknown logical state. So we have some unknown logical on the left, and we're going to use an ancilla encoded in plus to measure out one of the syndromes, and then an ancilla encoded in 0 to measure out the other syndrome. And the way this is chosen is that we're not actually learning the logical state. We're only learning the stabilizers. Of course, because we live in this terrible world that there's errors everywhere, each step of the circuit can incur additional errors that can flow back onto the system. So I've indicated those by these orange and black arrows. And I should mention that there have been some recent experimental implementations of doing Steen error correction for, like, say, a repetition code or a color code, including by some people in the audience. Okay, and so the thing is, because there's this backflow of errors each time, so going back to this picture, if we were to imagine that our ancillas were noisy and this measurement process is noisy, but we started out with some completely pristine logical state, then through this process, it can be degraded. So even though we're using this process to learn the syndrome, we can actually, if it's too noisy, then this just completely backfires. So when I say quantum memory, what I'm saying is, let's see if we take this pristine system, now subject it to some number of rounds of Steen syndrome measurement, say NT of them, and then some final round of perfect stabilizer measurements. To make our lives easier, let's just do heralded errors for the purpose of this talk so we can optimally decode. And so what we see is, okay, first we can try just one round, and we get this threshold. So we can see that in the sub-threshold regime, again, the failure probability is going down with the system size. Then we can say, well, we really wanted to survive some time that is actually scaling, growing with the system size, right? Because if we have a bigger code, then the idea is that we're going to want to perform a deeper circuit. So we took n of t to be equal to the code distance, and once again, we get a threshold. So this shows that logical information can survive many rounds. The other thing that we did in theory is look at magic state preparation. So in principle, if we want to perform, say, a logical T gate, then what we could do is prepare a logical T state and then use it for T gate injection. So for for this protocol, we can't actually use this multi-tree thing because it's not in the X or Z basis. So what we can do instead is use that bare tree encoding, which luckily we know has this coding phase. And so that has this, so if we just run the bare tree, we get we can look at the fidelity to the logical T state, the ideal logical T state. And as soon as we turn on E, so E is the erasure rate, as soon as we turn that on, the fidelity is going to be less than 1 because we're not doing a fault-tolerant protocol for preparing it. But we can then feed it into a state distillation protocol. And using the protocol in Bravi and Kataev, there's a threshold above which you can successfully do distillation. And we find that in this entire coding phase, so along this black line that I've shown, we're above that threshold. So we can successfully do magic state distillation. So with that, I'm going to conclude. I told you about some steps that we took towards universal fault-tolerant computation using concatenated codes. These are nice, tiny, the base code is only 2 qubits, so we can get to pretty large depths, even on a relatively modest system. Even a small number of qubits, we can already have, like, say, 5 generations. I showed you how we did state preparation without extra ancillas or without even post-selection. And again, I'd like to mention that although fully heralded errors are unrealistic, partially heralded noise is particularly relevant in today's experimental platforms. And with that, I'll conclude. Thank you.
Do you have any questions?
You mentioned fault tolerance many times, but the error model was independent bit flip and base flip. So I was wondering if your theory could consider at least the errors propagating throughout the circuit.
Sorry, I couldn't hear the last part of that question. You said
I was
independent.
wondering if your theory could at least capture errors propagating throughout the circuit.
You know, so the errors are propagating. They occur like locally, but then of course they're propagating through the circuit. Like. You mean, are you asking about correlated errors or?
Yeah, but like the second bullet point is state preparation without ancilla overhead. And is that enabled within an error model where errors can actually propagate?
I guess I'm just confused because errors are propagating. They're just occurring locally. I mean, you could have like, okay, it would be harder if you had like some really distant correlated errors. Like it would make my life harder, but what we're doing is already fault tolerant. So I'm somewhat confused by the question. Maybe we can talk afterwards.
I think the question is about like C0 errors. So if you have C0 errors in your model, basically.
Yes, okay, so we have, so maybe a slight simplification is that, just for the purpose of the analysis, if we have a C0 gate, what you might do, like what might occur in actual experiments is that the error that occurs due to that C0 gate is like correlated between those two outputs. We could have done that. Actually, I did do some numerics on the case where it's erasure errors, but for the purpose, like that's just like a sort of a detail, like between 2 or 1. Like, I mean, so what I do is after a 2-qubit gate, I just put independent errors on each of the outputs. But there are gate errors happening. They're just not, maybe the model is slightly simplified from what might happen in the experiment.
Do you have some model for the error that you expect to see as a function of the erasure rate, at least? And if so, could you use that model to extrapolate the data at low errors and see how much deviation you have to potentially reveal something about the hardware?
That's an interesting idea. So, yeah, I mean, like I can do simulations to larger system size, or sorry, I can do simulations at smaller erasure rates and see how that, like I can compare the classical simulation to the actual hardware. I just, that's not something I've done, but yeah, that would be an interesting idea. I guess the thing is though, at least with the data that we could collect, I mean, the errors are being dominated by the stuff that we're adding in, so we already know that. But yeah, if you could like get good enough statistics at small added error rate, then you could maybe see deviations between the model and the actual hardware.
Sorry, I think I maybe got confused in the beginning, and maybe you can just clarify this. So you did say that there are correlated errors. Just if you consider the single tree model where you have a couple of insulas and then you're sort of growing it by doing some kind of gates in between. I'm a bit confused how you don't get errors that, like, if there are correlated errors at the end, you should be getting more errors than you started with if you're doing CNORs within the same layer. Like just considering the single tree model, not the multi-tree.
You know, so it's true that if you're in this and you put an error in the beginning, it will spread to something big. But at its birth, it was just a local error. So like you're not actually, so the way that you do the decoding of the single tree, of course the errors that you see at the leaves will be correlated, but you can basically contract this tree tensor network with just including the local errors, like where they got spawned, and then it's not a problem that they got spread. It is miraculous that there is even in the single tree, there is a phase with where you converge to like some finite failure probability. That has to do with sort of the wonderful things that can happen when you do StatMech on trees. But that's the subject for another talk.
Okay, let's send the speaker again.